Welcome to this lesson on recognizing handwritten digits using Scikit-learn. Recognizing handwritten digits in Scikit-learn. This lesson will help you understand how computers can recognize handwritten digits using Python. You will see every step from loading real-world data to creating and evaluating a simple machine learning model. We use the digits dataset built into Scikit-learn, a standard tool for this kind of problem. Almost anyone can relate to digits, so it is a friendly way to get into data mining and machine learning. Even if you have never used Python before, you will follow along and get results by the end. If you are finding this useful, remember to like and subscribe for more beginner-friendly videos. Running the cell now. Let us get started by setting up the environment. First, let us keep our output clean by hiding warning messages. This helps beginners focus on the essentials and not worry about technical text during the lesson. #suppress warnings for a clean notebook. Import warnings, warnings.filter warnings, ignore. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. In this step, we set a random seed and suppress warnings to ensure our results are consistent and our notebook stays clean throughout the lesson. Although there is no visible output, this setup is crucial for reproducibility and focusing on the key concepts as we work with the digits dataset and build our model. Now the notebook environment is ready and free of distractions. Next, let us load the dataset we need for recognizing handwritten digits. Data setup. We use the built-in digits dataset from Scikit-learn. Each digit is an image with 8 by 8 pixels. The problem is to predict which digit is shown in an image. All data is small, free to use, and needs no download. Running the cell now. Let us load the data and inspect what it looks like. We are loading the classic handwritten digits dataset. In this dataset, each number is represented as an image. Let us print out the size of our features and what we are trying to predict. #load the digits dataset from Scikit-learn. From Scikit-learn.datasets import load_digits. Digits equals load_digits. X, Y equals digits.data, digits.target. Print x.shape. Print y.shape. Running the cell now. Here, the output shows that our feature matrix X has 1797 samples, each with 64 features, corresponding to the 8 by 8 pixel values flattened into a vector. The target array Y also has 1797 labels, one for each image, confirming that the dataset is balanced and ready for supervised learning. This setup verifies that our data is properly structured for training a digit classification model. Our data is now ready. X contains the flattened pixel values. Y is the correct label for each digit image. Let us look at how the raw data appears as numbers. Each row is one image stretched into a list of numbers. These are 64 features per image, one for each pixel. #display the first 5 rows of data. Import pandas as PD. df equals PD dataframe, X. Print df.head. Running the cell now. Here, we convert the image data into a dataframe and display its first 5 rows, revealing 64 columns that represent the 8 by 8 pixel values of each digit image. Notice how each row corresponds to one image, and pixel intensities range from 0 to 16, capturing the grayscale shades. This setup is key to preparing the raw pixel data for analysis and modeling in our digit recognition task. You can see the first few digit images as numbers. But these numbers alone do not make it easy to know what each digit is. To make things less abstract, let us actually draw a few digit images. Visualization helps you see what the computer will learn from. Each little square is an 8 by 8 picture showing a handwritten digit. #visualize some sample digit images. Import matplotlib.pyplot as plt. Fig axis equals plt.subplots 1, 5, fig xy sad smiley 10, 3. For I, ax in enumerate, axes. Ax.ims how, digits.images, I, kmap equals gray underscore r. Ax.set underscore title, f label, digits.target, I. Ax.axis, off. plt.show. Running the cell now. Here, we visualize 5 sample digit images from the dataset, each labeled with its true digit. Notice the 8 by 8 pixel grid forming each image, showing how the raw data appears as grayscale patterns. This helps us understand the input format and the challenge of recognizing digits from these small images. Now you can see what some handwritten digits look like to the computer. This visual taste is important before diving into modeling. Let us step back and talk about why digit recognition is actually so interesting. Why recognize digits? Digit recognition is a classic problem in data science and artificial intelligence. It connects to real-world things like sorting post, bank checks, or reading utility meters. Successful digit recognition is the first step towards reading handwriting or even documents. Machine learning is the tool we use to teach computers to spot digit patterns. Running the cell now. Let us continue by preparing the data for our first digit classifier. It is good practice to make sure there are no missing values. Missing data can break machine learning models or give unreliable results. Let us check if there is any missing information in our images. Check for missing data. Import numpy as np. Missing equals np.isNan x.sum. Print f total missing values, missing. Running the cell now. This output shows that the dataset has 0 missing values, meaning all pixel data for the digits is complete. This is important because missing data can disrupt the training process, so confirming no gaps ensures our machine learning model will learn from fully intact digit images. If you see 0, everything is complete. That means every image is ready for machine learning. Before we build a model, we need to set aside some examples for testing. This is the train-test split. We teach the model on training data and see how good it is on testing data it has never seen. Split the data into train and test sets. From scikit-learn.model_selection import train_test_split. x_train, x_test, y_train, y_test equals train_test_split, x, y, test_size equals 0.2. Random_state equals 42. Print x_train.shape, x_test.shape. Running the cell now. The output shows the shapes of our training and testing datasets after splitting the digit images and labels. We have 1,437 samples for training and 360 for testing, each with 64 features representing pixel values. This split is crucial to teach the model on one set of digits and evaluate its accuracy on unseen data, ensuring it can generalize to real-world digit recognition tasks. 80% goes to training, and 20% is for testing generalization. Let us check if every digit class is present in our training samples. Balanced classes make sure our model learns all digits and does not skip any group. Look at the label distribution in the training set. Unique, counts equals np.unique, y_train, return_counts equals true. For value, count in zip, unique, counts. Print, gef, digit, value, count, samples. Running the cell now. This output shows the number of training samples for each digit from 0 to 9, revealing a fairly balanced distribution across all classes. Noticing this balance is crucial because it means our model will have enough examples of each digit to learn from, which helps improve its accuracy in recognizing handwritten digits. This step ensures the dataset is well prepared for training a reliable machine learning model. Here you can see that all digits from 0 to 9 have roughly equal samples. That is important for fairness and learning. Scaling feature values can help machine learning models work better. Standard scaling turns every feature into a value with 0 mean and unit variance. This will improve the accuracy and stability of our next models. Scale the features for better model performance. From Scikit-learn. Preprocessing import standard scalar. Scalar equals standard scalar. X_train_scaled equals scalar.fit_transform X_train. X_test_scaled equals scalar.transform X_test. Running the cell now. This code scales the feature data, adjusting values to have a mean of 0 and a standard deviation of 1, which is crucial for improving model performance. Although there's no visible output, this transformation ensures that each pixel intensity in the digit images contributes equally during training, helping the machine learning algorithm learn patterns more effectively. Scaling is a key step before feeding data into models, especially for digit recognition tasks. Now both training and testing feature sets are scaled. This prevents large numbers from overpowering the model. Let us move from preparation to modeling. This is where your data mining skills start doing real work. Building your first digit classifier. The most basic classifier is called logistic regression. It is a simple algorithm that learns boundaries between groups. Logistic regression works for digits because it can handle numbers as categories. The steps below will fit a model to the training digits. Running the cell now. Let us try this approach on our prepared digit images. We are now training a machine learning model to spot digit identities. Logistic regression can learn lines that separate one digit from another. Max_iter is the maximum number of passes over the data. Multi_class means we allow more than 2 output classes, since there are digits 0 to 9. Train a logistic regression model. From Scikit-learn. Linear_model import logistic regression. CLF equals logistic regression, max_iter equals 1000, solver equals LBFGS, multi_class equals auto, random_state equals 42. CLF fit X_train_scaled Y_train. Running the cell now. This output shows the logistic regression model after training, confirming it has been initialized with 1000 maximum iterations and set to handle multiple classes automatically. Notice that the model is now ready to classify digits based on the training data it has learned from. This step is crucial as it means the classifier has found boundaries to separate different digit categories effectively. Our model is now trained and ready to make predictions. It is time to use the trained model to recognize new digit images. We will look at the first few predictions to see what digits it thinks are present. Predict on the test set. Y_pred equals CLF predict X_test_scaled. Print Y_pred 10. Running the cell now. Here, the code uses our trained logistic regression model to predict the labels of the first 10 test images. Notice the predicted digits, like 6, 9, and 3, showing the model's ability to classify varied handwritten numbers. This output confirms that the model is assigning digit categories based on the features it learned, which is the core goal of fitting a classifier. Here are the model's first 10 guesses. Let us measure how often it gets the right answer. Accuracy means what fraction of test digits are recognized correctly. If our accuracy is high, our model is doing a good job at digit identification. Measure model accuracy. From Scikit-learn. Metrics import accuracy_score. ACC equals accuracy_score, Y_test, Y_pred. Print F accuracy, ACC 0.2F. Running the cell now. The output shows an accuracy of 0.97, meaning our logistic regression model correctly classified 97% of the test digits. This high accuracy indicates that even a simple algorithm can effectively learn boundaries between digit categories. It confirms that logistic regression is a solid first step in building a digit classifier. A score above 90% is already pretty strong for basic digit recognition. We can dig deeper and see how well the model does on each specific digit. This helps spot if it is confusing one shape for another, like 8 and 9. Show model performance for each digit. From Scikit-learn.metrics import classification_report. Print classification_report, y_test, y_pred. Running the cell now. This classification report shows the performance of the logistic regression model on each digit, highlighting precision, recall, and F1 score for all 10 digits. Notice the high scores, mostly above 0.94, and balanced support counts, which indicates the model is accurately distinguishing between digit categories. This confirms that even a simple logistic regression can effectively learn boundaries in digit classification tasks. Now you see the precision, recall, and F1 score for each class. These tell how well each digit is detected individually. Precision is how many times the model predicted a class and got it right. Recall is how good it is at catching all real cases of a digit. The F1 score is a balance between those two. Let us look at several test images and see how well the model matches the real answer. A picture is hard to argue with. Visualize results, show predictions versus actuals. Fig axis equals plt.subplots 2, 5, fig size sad smiley 12, 5. For I, axin enumerate, axis.flat. idx equals I. ax.ims how x_test, idx.reshape, 8 late, kmap equals gray_r. ax.set_title, fpred, y_pred, idx, true, y_test, idx. ax.axis, off. plt.tight_layout. plt.show. Running the cell now. This visualization displays 10 test-digit images alongside their predicted and true labels, allowing you to directly compare the logistic regression model's guesses to the actual digits. Notice how the model correctly classifies most digits, demonstrating how logistic regression can learn decision boundaries even with simple features. This step helps confirm the model's effectiveness before moving on to more detailed evaluation metrics. Above, each digit is shown with the model's guess and the real answer. If they match, the recognition is correct. Here is an idea for your first experiment beyond this notebook. Bonus: try your own digit. Did you know you can predict your own data if it matches the digit's format? Just reshape your 8x8 gray pixel image to a 64-element array. Feed it through the scaler and model, and see what comes back. This is a mini project you can try for practice after the video. If you want more beginner-friendly projects, do not forget to subscribe. Running the cell now. Mini project: make your own 8x8 digit drawing as a grayscale image, flatten it into 64 numbers, and have the model guess what you wrote. A confusion matrix shows us exactly where the model is mixing up digit classes. Rows are real labels, columns are guesses. Ideally, all the mass is diagonal, meaning perfect prediction. Confusion matrix: where does the model get confused? Import Seaborn as SNS. From Scikit-learn.metrics import confusion_matrix. CM equals confusion_matrix, y_test, y_pred. plt.figure, fig size sad smiley 86. sns.heatmap, cm, anat equals true, fmt equals d, kmap equals ylgnbu. plt.xlabel, predicted. plt.ilabel, true. plt.title, confusion matrix. plt.show. Running the cell now. Here we see a confusion matrix heat map that highlights where the model correctly predicts digits and where it gets confused. The diagonal cells show high counts, indicating accurate predictions, while off-diagonal cells reveal specific digit pairs the model struggles to distinguish. This visualization helps you understand model performance before trying it on your own reshaped digit image. Areas off the diagonal tell you which digits the model confuses, such as 3 and 8. Spotting these can guide your data cleaning or choice of a new model. Now let us see if another algorithm might do better. K nearest neighbors looks at the most similar training digits to make a decision. Sometimes, this method can handle weird shapes a little better. Try a different model, k nearest neighbors. From scikit-learn.neighbors import k-neighbors classifier. knn equals k-neighbors classifier, n_neighbors equals 5. knn.fit, x_train_scaled, y_train. knn_pred equals knn.predict, x_test_scaled. knn_acc equals accuracy_score, y_test, knn_pred. Print f knn accuracy, knn_acc 0.2f. Running the cell now. Here, the k nearest neighbors model achieved a high accuracy of 0.97, showing it can reliably classify the handwritten digit images. Notice how this supports the lesson's idea that once a model is trained, you can confidently feed your own reshaped and scaled digit data to get accurate predictions. This output encourages you to try predicting your own digits as a practical next step. Compare both accuracy numbers and see which model you would choose for your own tasks. Let us plot how many samples we have for each digit. This is a simple time series style visualization that checks for balance in the dataset. Balance matters for fair training and realistic results. Time series, visualize digit count over index. Import matplotlib.pyplot as plt. Digits_per_index equals pd series, y.value_counts.sort_index. plt.figure, fig size sad smiley 84. plt.plot, digits_per_index.index, digits_per_index.values, marker equals low. plt.title, sample count by digit value. plt.xlabel, digit. plt.ilabel, count. plt.show. Running the cell now. This plot shows the count of each digit class in the dataset, rising and falling to reflect how many samples exist per digit from 0 to 9. Notice the variation in counts. This helps understand the data distribution before you try predicting your own digit image. The code's intent is to visualize class balance, which is crucial for evaluating model performance and bias. There are close numbers of samples for each digit 0 through 9. If you see large imbalance in your own dataset, address that before training. Well done for making it through this beginner lesson. Let us go over what you accomplished. Congratulations! You built a digit recognizer? You saw practical machine learning from start to finish. Using Scikit-learn, you loaded, visualized, split, scaled, and modeled data. You picked a model and verified its predictions. You learned about confusion matrices, model accuracy, and alternative algorithms. This is a foundation for all kinds of pattern recognition tasks. Do not forget to practice and try tweaks. See the YouTube video description for more exercises and helpful resources. Running the cell now. Thanks for watching and learning with us. If you have questions, post in the video comments and we will do our best to support you. See you next time.